All right, let's get started. So today we're going to conclude our lecture, or our first lecture, I guess, first set of lectures on machine learning. And this is going to be about kind of the algorithms and the basic methods of machine learning. And then next lecture, Ariel will talk about the more theoretical aspects of machine learning. And then we'll actually spend quite a bit of time focusing on deep learning, which is a method for machine learning that's gotten a lot of attention in recent years. And so this set of slides is actually just an expanded version of the last one. So it's the same document, but I've just added more sections here. So that the slides on the website actually link to both. So what we're going to finish up talking about linear classification today. That was the setting we started last time, where we have, instead of the outputs being real valued quantities, they are now binary quantities that are either -1 or +1. Then we'll talk about nonlinear methods. And so far it seems, at least, like our methods we talked about so far are fairly limited in that they kind of only can represent lines, either lines separating classes or lines in predicting the output. But I'll show that with pretty simple modifications, you can actually make these same algorithms also work for the nonlinear setting, at least nonlinear in some definition of the word. And so they actually can be quite powerful. So I'll talk about that. And then I'll talk about, that will kind of lead us into a few other topics that are really important to understanding machine learning in general, which are ideas of overfitting, of generalization, and of regularization. And I'll talk about this from a very applied standpoint right now, and kind of a very intuitive, high-level standpoint, though I imagine that those similar things will be touched on the lecture on machine learning theory as well. And then finally, I'll conclude with some methodology on evaluating machine learning algorithms. So let's jump back into where we were last time. So where we ended last time was with the formal setting for classification. I just wrote that back up here. We have inputs, which we consider vectors in Rn. We have outputs, which are binary valued. We have some parameters, theta, which define our hypothesis function. In this case, for a linear classifier, we're going to assume we have the same number of parameters as the size, as the dimensionality of the input. But in general, when we talk about neural networks and things like that, that will not hold. We have a hypothesis function that maps inputs to real numbers. And this is a little different, because we weren't talking about mapping it to the output class anymore. We're talking about still mapping to real numbers, where that number, the real value number, corresponds to some notion of how confident we are that the quantity is either +1 or -1. So it's very positive, this real value quantity. We think we're very confident that we are +1. If it's very negative, we're very confident that it's -1. And kind of the picture to have in mind here, and this was on our breast cancer classification task, was think about linear classifiers as kind of drawing separating planes in the feature space. So they define a linear function, or linear classifiers, at least of linear classifiers, this function would just be still just like the regression case, h theta of x equals theta transpose x. And these regions are characterized by the red here is the place where this function is greater than 0, and the blue is the place where this function is less than 0. And so that kind of is how we think about separating hyperplanes in classification tasks. So what I want to spend some time talking about now is this loss function here, because in classification, this one here. Because in classification, or sorry, in regression, it's sort of very natural to think about loss functions, right? Well, how far is our prediction from our actual output we want to predict? And things like the squared loss or the absolute loss make a lot of sense in that setting. But in classification, it's not quite as clear what you want, at least in this setting here, where we're talking about predicting a real value quantity still. If you just predict the binary quantity, maybe you say, okay, if I'm either right or wrong, that's my loss. But it turns out that's actually very hard to optimize that loss. And so instead, we actually think about losses that map between our prediction space, which is the real numbers, and our actual output space, which is -1 and +1. And so the first question, I think, is why do we need different loss functions, right? Why can't we just use, these are, yes, they're just discrete, but they're still numbers, could we just still use the loss as something like the squared loss? Could we just use that still? And I think an example to show sort of why this is not maybe a good idea is as an example like this. So if we take those points and fit a minimized squared loss of those points, right, we get a function that looks like this. Again, this is exactly the same now as the least squares fit to these points. But in this context, what we're saying is that this is the least squares fit, but our predictions are going to be positive in the region where that function is positive and negative in the region where that function is negative, right? And it's hopefully pretty apparent that this is actually classifying one of these examples incorrectly, right? The one in the middle there is being classified incorrectly. The point is positive even though the function is negative. Whereas this is still a case, though, where we can produce a perfect classifier. So this is a different classifier that everywhere it's positive, the examples are 1, and everywhere where it's negative, the examples are -1. Right? And so the intuition here is that somehow least squares is trying to fit, if we use least squares with the 0, 1 errors, it would be trying to fit that point all the way on the right there as having the actual value of +1. Right? It doesn't really matter what that point's value is as long as it's positive. And least squares kind of misses this fact, right? Least squares says I'm going to try to actually approximate all my outputs well, even though that isn't really what we care about here. It doesn't really matter. All that really matters, in fact, maybe it's very good that we have that, the green classifier would be very good there because according to the green classifier, we'd be very confident that that point over there was in fact a +1. And the least squares loss just doesn't capture this. This is kind of the motivation for why we think about different loss functions in classification and why we don't want to just stick with the regression setting. So with that, I'll jump right into kind of the loss that probably all of you thought we should use from the beginning, even though you probably didn't write it this way, which is just the accuracy or the errors or the 0, 1 loss. And I'm going to draw it kind of in an odd way. So if we have a classification problem, a very natural loss function would be, well, we're wrong if we predict positive and the thing is negative, and we're right if and we're also wrong if we predict negative and the thing is positive, otherwise we're right. And so why don't we just count the number of mistakes we make and have that be our loss function? And that's something we can actually also express in this framework here, and it's called 0, 1 loss. And I'm going to draw it this way, and it's important to kind of look at this figure and see what this means. So I'm going to draw my loss function in terms of, on the x-axis, this is the 0 point here, and I'm going to draw on the x-axis the following quantity. I'm going to draw y times my hypothesis function. That's the x-axis of these plots here. And the reason I do that is this lets me actually express loss very naturally. And I'm going to say that my loss function that is just sort of counts the number of errors I make would be this one, where this number here is 1. And the reason why, you can just sort of check this, right? If my true label is positive and this is also positive, then I'm on this side of the graph here, right? So I have 0 error. And in fact, as I get more positive, it doesn't actually matter how confident I am. I'm still just getting 0 error. But if the signs of these two things mismatch, either if this is negative and this is positive, then I'd be in this region over here, right? And so I would actually suffer a loss of 1. In other words, this is just going to be, this is just an indicator of whether or not I made a mistake on that example. And one way of writing this is that this function, which I'm going to call the 0, 1 loss, 0, 1, as a function of my hypothesis and my output, is just the indicator of y times that thing being less than or equal to 0. Okay. So hopefully in a second it'll make clear why I'm doing this. Because this is kind of the most natural loss function for classification, right? And by the way, if we did this, we could then just define this thing as actually outputting 0, 1 values, because it doesn't matter, the sign there. You could just take the sign and call that your hypothesis function, and you can kind of be done. might be a lot easier classification. But there's a big problem with this loss function, and that is we can't actually optimize it. Actually, can anyone tell me why this is going to be hard to optimize, this loss function? If I want to minimize the sum of these things on a data set, why will that be hard? So up there. It's not differentiable. Okay. Neither is absolute loss. We can still, I mean, not at 0, right? We can still optimize that just as well. Yeah. Matthew, right? Michael, sorry.
It's not even continuous. So if you change something by a little bit, the loss function could jump.
Yeah. So it isn't continuous. That's true. That's maybe nasty, but you actually can define loss functions that aren't continuous that you can still optimize kind of okay. It's not always easy, but you can still optimize them. Looking for one more answer. Yeah. Yeah. So the answer I'm looking for is it's not a convex function. And it turns out that actually finding the classifier that minimizes this loss, in other words, minimizes the raw number of mistakes you make, winds up being an NP-hard problem. It's unfortunately, which seems like something we want to do, right? But we unfortunately cannot do that. It's in the same class as integer programming. It actually can be written as an integer program, but it's not something that's very easy to do because it's not convex. And by the way, the reason why it's not convex is that you can take 2 points here, connect them, and it does not lie below, the function does not lie below those 2 points, right? So everything else is nasty about it. It doesn't have very good gradients over here, right? You can't really tell which way you should go. Maybe it's also discontinuous, but you can have discontinuities with convex functions to infinity. As long as discontinuity goes to infinity, you actually can have that. So that's, maybe not that bad. The real problem is it's not convex, and as we know, therefore, we can get things like local optima and just have sort of general nasty cases here. And so what classification does really is that we look at alternative loss functions that in some sense try to approximate this function. And most classification algorithms actually, even ones that sound very different like logistic regression or support vector machines, those are actually just slightly different approximations in some sense to this 0-1 loss. So let's talk about what these things are, what these look like. So unfortunately, 0-1 loss is hard to optimize. It's NP hard to find a classifier with minimum 0-1 loss. I should say that means, in the worst case, if you let me pick my data set to be as bad as possible, it's NP hard. If you can find a 0 loss classifier, by the way, then you can do it. You can do it with actually by minimizing virtually any of these things will give you a 0 loss classifier. But in the worst case, it's NP hard. So a lot of these methods try to come up with alternative optimization procedures, alternative loss functions that are more amenable to optimization procedures that sort of are nicer in some sense. And so these list sort of a bunch of common ones. So the 2 probably most common ones that you'll see are called the logistic loss, which is defined like this. That is the green line here. So it kind of actually looks like the 0-1 loss if you squint your eyes a little bit. It doesn't actually look like it because it has to keep going up. In fact, I mean, it can't look like anything that does this, right? No approximation can kind of tail off this way because that would be non-convex then. So they have to, at the worst, keep growing linearly that way. And so all these losses are in some sense, convex approximations, though they look not like that good approximations maybe, but they are convex approximations to the 0-1 loss. So the logistic loss is this function here. It's the log of 1 plus the exponential of this thing. Again, notice they're all actually written in terms of this quantity, y times the hypothesis function. So we can all plot them on this same plot where that's on the x-axis. The other really interesting one is the hinge loss. The hinge loss is the max of 1 minus that thing and 0. So that's a function that looks like a linear function that passes through the 0-1 point, but then once it hits 0, it stays at 0. And so it's actually really important to interpret what these losses mean. Remember, and in some sense they actually might be nicer in some ways than the 0-1 loss even. So remember, when we go this way in the graph, we are becoming more and more confident in our predictions because we're having a higher magnitude of our hypothesis function, yet we're also wrong because the signs between our actual output and our prediction don't match. And so if we're really wrong, yet also, if we're really confident, but yet also wrong, we should in some sense suffer more penalty than if we're only a little bit confident and we get it wrong, right? So all these loss functions, they actually increase as you go more and more this way. And so that corresponds to the intuition that as we become more confident but are wrong, we pay a higher and higher penalty. Some of them, not all of them, will actually, they all go towards 0 as you get more and more confident and you're right, but actually some of them, the hinge loss actually does hit 0 and stays 0 exactly, whereas the other losses just go to 0 very rapidly. But again, those two at least, the hinge loss and the exponential loss maybe will actually penalize you a little bit even if you're right. But as you're more and more confident and you're still right, they penalize you less and less. So that's the intuition here. So right here, actually all of them will give you a little bit of penalty even though you are right, but they give you sort of less and less penalty as you get more and more confident in your correctness. So the nice thing about this formulation, I would say, is that with this sort of in hand, we really can treat classification and regression identically. There's no difference from the standpoint of optimization or the formulation of the machine learning problem. In particular, the optimization problem we actually want to focus on is still exactly the same. It is that we want to minimize over our parameters theta the sum over all the examples in our data set of the loss of this example and the true output. And that's still our objective, and we can still solve it with methods like gradient descent. For these classification losses, none of them actually have closed form solutions. So least squares is almost the only algorithm where you can write a closed form solution for the optimal theta. The rest you have to apply some iterative method like gradient descent. And so here, for most classification, we're actually going to use gradient descent to actually update our parameters. There are certainly fancier methods. If you've heard of things like Newton's method, that's another optimization method, which is actually common for some of these things, but gradient descent actually is kind of the workhorse of a lot of machine learning still. So let me now sort of define a few algorithms for you. And you may have heard of these things before, but you may not have heard of them in this context, sort of presented this way before. So who here has heard of a support vector machine? Okay. So support vector machine is just this thing, minimizing this, where you use hinge loss. That's what it is. I actually should say there's a slight addition where you actually also add a term called a regularization term, which we'll talk about this lecture. It says next lecture, but now it's this lecture. But that's all it is. It's just minimizing hinge loss. You may have seen it in terms of the geometric interpretation where you're maximizing a margin, which is true also, but I think it's actually nicer to think about it in this way because it sort of connects all the different algorithms. So now if we actually run a, and by the way, this is the gradient of the support vector machine. You can see that because the hinge loss here, I'll mention a little bit. So the hinge loss looks like this. The 0.1. So the gradient of just the loss function there is a -1 in this region and 0 in this region. So that's this indicator times the negative sign there. And then you pull out the x and the y when you differentiate with the chain rule. So not covering that too formally there, but that ends up being the gradient of the support vector machine of the hinge loss. And to find the solution, you just iterate that with some small alpha, with some small alpha. And what you get is you get something like this. So this is our decision boundary with a support vector machine on our tumor cancer data set. And it kind of does what you would expect, right? It minimizes the loss on these examples. Here you cannot actually separate these classes exactly, given this. Obviously, there's no linear classifier that would get all the red examples on one side and all the blue examples on the other side. But as you may imagine, this is, and this looks like a pretty reasonable separating plane, right? This is the plane that minimizes the sum of these losses over this data. And the coefficients that do so are right there. The first term is the, I've actually normalized these a little bit. So actually, I forget if I did now. I take that back. I don't know if I normalize them or not. I think so, though. But essentially, the first term is the weight on the first coefficient, maybe scaled some way to make them a little bit numerically more stable. And the second weight is the weight on the second coefficient. And then the third one is a constant offset term, or the weight on a constant term. And just to sort of show how this kind of works in practice, maybe, what I'm plotting here is when I run gradient descent on this method, this is a plot of my iteration number of gradient descent versus the loss that I suffer. So when I start off with some initials, it doesn't actually matter what you pick as your initial solution. It could be 0. I think I picked 0 here, just the vector of all zeros. And I run this and I plot my loss over the different iterations. I get something that looks like this. So we start off with a very high loss. Pretty quickly kind of start to decrease our loss by taking gradient steps, and then finally we converge to the solution there that has a loss of around a little bit more than 100. Again, what that loss actually is in terms of the numerical quantity here isn't really that important because it's this thing. Where is it? I didn't write it down, but it's hinge loss. It's the max of 1 minus h theta x and 0. Sorry, y times h theta x and 0. Now, what that exact quantity is may not matter that much. It actually ends up being, kind of interestingly, ends up being an upper bound on the number of mistakes you make, precisely because this function is actually an upper bound on the 0, 1 loss. So we don't know what the hinge loss really corresponds to, but we do know, maybe of interest, is that it's actually going to be definitely higher than the number of mistakes you make. Could be a lot higher if you have some examples way over here, but we know it's higher. It's actually the smallest convex upper bound for the 0, 1 loss. Smallest convex function you can find that is an upper bound on that function. So it corresponds to some sort of level like this, where we get this near loss. And then also interesting to see, separate from this in some sense, is the average error. So this is the 0, 1 loss I'm plotting now. I should say the mean 0, 1 loss is just the number of mistakes we make in our data. And usually for classification tasks, this is the metric you actually report. You want to minimize this, but you choose to minimize one of the other loss functions because you can't actually minimize that. And one thing that's kind of interesting here is that we see that this average error bounces around a lot kind of in conjunction with minimizing the loss, but actually after even just a few steps it's already at less than 10% error, and then after a lot of steps it sort of converged to 8.8% error, where it starts off even after one gradient step with 10% error. So it's very interesting to compare, and I won't say more about this, but it's very interesting to compare. And also, by the way, the final point you converge to is not the point with lowest 0, 1 loss, right? There actually is a point that gets one fewer mistake than the optimal point, but that's a artifact of the fact that we are not actually minimizing 0, 1 loss. We're minimizing this other surrogate loss that may or may not actually be minimizing what we want to minimize. So just a point to keep in mind that it's useful to think about both these two things when you look at the progress of an algorithm. Let's talk about another algorithm now, which is logistic regression. And that is actually now very similar. It's just that instead of minimizing the hinge loss, we're going to minimize the logistic loss, which is this function here, the log of 1 plus the exponential. If you plot it, you can kind of actually see that it's in a lot of ways very similar to the hinge loss. As you go very far negative, right, you have log of 1 plus something really big that's negative there. So that would be, and because this thing is negative, the exponential of that is positive, or the negative of this thing is positive. So take the exponential of a big positive quantity, and you take the log of that. So that's almost just like negative y times h theta x. So it's almost just, negative of that. So it's almost just a linear line as you get up more and more negative. And then as you go to more and more positive, it becomes essentially almost 0 because you have getting closer to the log of 1, and so you're becoming essentially 0. And it's kind of unlike the hinge loss, which has this non-differentiable point right there, logistic loss is a smooth function that sort of smoothly goes between going to 0 and then becoming a linear function as you move more and more to the left here. And this leads to a very sort of, again, classical algorithm called logistic regression. I should say that this one in particular has a very nice probabilistic interpretation. And I haven't mentioned probability at all so far in some sense, which seems kind of crazy because probability and machine learning are very intertwined. But I'm actually going to defer all that to later lectures when we talk about probability. So there is a probabilistic interpretation to this, but we're going to just kind of ignore that and think of logistic regression as just a method that minimizes a slightly different loss function. And in fact, if you look at these things, here is the minimum we attain when we run logistic regression on this data set, and here's what we attain when we run a support vector machine. So not a whole lot of difference there. Sorry for the slide timings. I know that's going to screw you up, JT. Every time I change slides, it records the timing that I did that. But I want to emphasize this point actually, because I think this point is one that is lost a lot. And that is these different algorithms that sound very different. So if you've seen another machine learning course maybe, or in some other course, logistic regression and support vector machines, they were probably presented to you very differently. One was this geometric method that sort of maximized the margin between the separating hyperplane and the examples, and one was this probabilistic method that was sort of giving a probability of the output given the input. And those are both actually, which we won't go into those details, but those are actually both true interpretations of the methods. But I think it's more useful to think about just how similar they are. They're just both minimizing some loss function that approaches linear as you get worse and worse, and approaches 0 as you get better and better, or becomes 0 actually. And so the difference in these algorithms is actually not that much. They're very similar. They have weird baggage associated with them, like support vector machines usually are also applied with kernels, which is a particular type of nonlinear approximator. But you can apply kernels with logistic regression too. There's nothing stopping you from doing that. So all these things are actually are really quite similar, the algorithms here. And it's worth noting that all they are doing still, even though they have fancy interpretations, is they're just minimizing the sum of some losses on our data set. And that's what really all machine learning is ultimately doing. Okay, so any questions there? Okay. I'll make one more note of something I haven't covered yet, and this is the only slide I have on this. But this is actually multi-class classification. So far I've covered the case of binary classification, where you have classes that are either -1 or +1. And when you have instead a discrete choice where you have to predict one of k different values, things are a little bit different. So this is like the digit classification task, where we want to predict whether something was a 0, 1, 2, 3, all the way to 9. And that's still classification, by the way. It's not regression, just because they happen to be numbers. There's no smooth loss between like the image 0 and the image 1. So you think of them as different discrete predictions that you're making. And there really are two approaches. Or there's a lot of approaches actually to multi-class classification, but the two of the most popular ones are first, you actually can just reduce it to binary classification. So you can set up problems where I want to classify something as either a 0 or anything besides a 0, and then a separate one for is this a 1 or anything besides a 1, etc., all the way up to 9. And then again, if you just had sort of binary predictions from your hypotheses, if you now ran it on a new example and everyone said yes, it's a 0, you wouldn't really know what to do. But fortunately, because our hypothesis class actually outputs real numbers, it's kind of obvious what to do. You just take the class label where the classifier is most confident. So you take the biggest of the different classes of whatever hypothesis produces the biggest output. You take that one as the predicted class. So that's a standard way of doing multi-class classification. The other thing you can do is you can actually define a different hypothesis function and a different loss function. So for example, you can actually define your hypothesis function to, instead of outputting single real value numbers, to output k-dimensional vectors, where k is the number of classes you have. And then in that context, what you sort of think of is you think of these different outputs are kind of measures of confidence I have in each of the different classes. So if the entry in the first item is really big, that would correspond to being very certain it's a 1. And if 2 are very big, if the number 2 is very big, that's very certain it's a 2, or maybe starting at 0, however you want to order the numbers, and do it kind of that way. And here you need a different loss function, though, right? Because our loss functions before really mapped from real numbers and then a binary output to a real positive number. And now because you have your outputs in 1 to k and your hypothesis function outputs in RK, you need a different loss function. So for example, there are things like one of the most common ones is called softmax loss, or also called cross entropy loss. And that is just a loss function defined between vectors in RK and elements 1 to k. And it's this thing. It's the log sum exponential of all the different hypotheses minus the hypothesis function at that true value. Why it is, I won't go into that. It actually ends up being a very similar derivation as with logistic regression. It ends up being actually a very nice generalization of the logistic loss to the multi-class setting, though that's not really that obvious there. But maybe a little bit, right? Because you can kind of think of a 1 being kind of like some of the other things there. I don't know. You can figure that out. Okay, so you actually might have some of that on your homework, but we'll describe it more when you do have it on your homework. So yeah. Mm-hmm. So the question is one approach better than the other? Not really. Some might perform better than others in terms of accuracy or not. This one's a little bit more common because this one actually can also be interpreted as things like defining a probability distribution over which class it is. I haven't talked about that yet at all. I will mention a little bit of that when we talk about probabilistic modeling. But it's a little bit more common to do the second one. The other thing is when we talk about neural networks, it turns out people usually do the second one in neural networks. And you actually use this one single network to compute all this hypothesis to compute your entire hypothesis function, as opposed to needing to have k different networks that compute different functions, right? That would be a lot more complicated seemingly. Whereas the last one, you can kind of get away with one network, where only the very last layer of the network ends up having more functions, more outputs than as a single binary class network. Don't worry about that, by the way, if that doesn't make sense, because we haven't talked about neural networks yet. We'll talk about those in 2 lectures. But typically, people do the second one. It's a little more common. Yeah? Sorry, I couldn't quite hear that. How does the first one interact with multinomial logistic regression? So I think this is the same thing as what you're calling multinomial logistic regression. It's the same loss function. Again, often written down or derived a very different way. It's just a loss function from the perspective of machine learning. It's also called softmax regression or a lot of other things, but it's just this loss function. Okay. No more questions? All right. In that case, we have a lot more slides to get through. A lot of them are pictures, though, so I think it won't be too hard now. We're going to move on now, then, in that case, to talking about nonlinear methods. So as I mentioned at the beginning of class, these things seem rather limited, right? Because though it seems great, we have this nice framework for all of machine learning. It's the same for classification as regression. We just apply gradient descent updates. It seems like all we're doing is still creating linear classifiers that just fit data to a line or create a line that separates 2 different classes. And that seems very limiting, right? There's plenty of data that does not seem to lie on a line. And in fact, as a case in point, I'm going to return to my original example I had about comparing the peak demand, peak electrical demand, to high temperature. And what I kind of said, but maybe seemed a little bit cheating in some sense, was I said this is only for the summer months I'm showing this, right? Because in the summer months we know that consumption is driven largely by air conditioning. So that's what people use in the summer. And so the hotter it is, the more power you use. But if we extrapolate downwards here with our linear regression plot that we had, it would say that if the temperature gets cold enough, people are actually going to start generating power. It must be, right? That we just start getting so cold that we start generating power, which is not really what happens, of course. What happens is actually this. So this is now the peak demand versus temperature for all months. Again, actually in Pittsburgh. This is peak demand in gigawatts and high temperature in Fahrenheit of the Pittsburgh of the region right around Pittsburgh. And what happens is what you expect, right? At a certain point, you don't keep decreasing your load. It sort of tails off. And in fact, as it gets colder, it starts increasing a little bit more. maybe that's due to needing more light in the winter when it's cold, or some people do have electrical heat, even though most heat is gas. Some people have electric heat and they pay an amazing amount of money in the cold winters in Pittsburgh. But anyway, if you try to fit a line to this, it looks quite poor, right? No one would say that that's a good model of what people are actually doing. And so when people say things like linear regression, the first thing in mind is that, well, you couldn't fit this with linear regression because it's not a linear function. But the crux here, and this is really why linear regression, despite having some limitations, and we'll get to those in a second, or maybe we'll talk about this a little bit when we talk about deep learning, is actually perfectly capable of representing things like this, just with one little trick. And so the trick, this is really what we mean today when I say nonlinear classification or regression, is that we're going to do linear regression, but we're going to do it on nonlinear transformations of the underlying data. Right? So when I defined my setting there, I just defined xi as my inputs. Implicitly, kind of, that was saying that this is, the actual variable that you're trying to, that is underlying your data. That was the input. But really, we could take any feature of that data and just make that our input. Okay, so we could just take, instead of just the high temperature, we also add a feature of the high temperature squared to our input. And now we have, the constant term, the high temperature, and the high temperature squared, comprising a vector that makes up our input. And very importantly now, our hypothesis function is still this linear guy here. So our hypothesis function is still linear in theta, our parameters, even though it's not linear in the underlying input x. Right? And so because of this, because linearity in theta, or rather, all we were doing when we fit the model is optimize over theta, nothing actually changes in any of our algorithms if we do change our input to include high temperature, a term with high temperature squared, etc. The algorithm, everything stays the same. And so, for example, we still have the same least squares solution of theta equals x transpose x inverse and x transpose y. Right? So we can kind of keep playing this game where we just add more and more inputs to our system. And in fact, if we maybe we take, x high temperature squared, high temperature cubed, etc. And we can get more and more expressive functions over our kind of original input space, which is just the high temperature. So if we take a polynomial of degree 3 now, so this is a polynomial where our features, sorry, I shouldn't really say polynomial. This is a linear function in theta where our features here were the high temperature of that day I, all cubed, the high temperature, squared, the high temperature, so the one just itself, and then a constant term, which actually also, by the way, is just the high temperature to the 0. That's our feature vector, right? And so our linear hypothesis function, though it's still linear in theta, is actually now a third degree polynomial in the temperature itself, right? So our hypothesis function, which is equal to theta transpose x, is actually equal to, where this x, this is actually the vector x that comprises all my inputs, is actually equal to sort of, theta 1 times, I should differentiate between these two things, times like x tilde, that's the original input. I'm not going to use this notation anymore, I'm just writing it here, cubed plus theta 2 x tilde squared, etc. Okay? So where x tilde just means the actual high temperature. And so if I plot then the resulting classifier against my original high temperature, it looks something like this. And so what we're able to do is actually capture nonlinear functions in my original inputs using still the entire framework of linear regression. And I can do it for the least squares case, but I can also do it for any other loss function as well, right? So I can do the same thing with classification, with absolute loss and regression, etc. And it all ends up being kind of the same methodology. All right, any questions there? Yeah.
So if you have multiple features,
Yes.
you're going to take like all combinations.
Yeah, so if you create sort of generic polynomial features, when you have multiple underlying features, like is it in the breast cancer example, like the mean area, plus the the mean number of concave points, then yes, you would take something like, and again in my original space, you'd have something like x1 squared plus x1 x2 plus x2 squared plus x1 plus x2 plus 1. That would be a set of all of a generic second degree polynomial over 2 dimensions. So yes, we won't dwell on this too much because the reality is polynomials don't end up being that great an approximator. You can use them occasionally, but usually, for reasons we'll show in a second, you don't necessarily want them. And also with higher dimensions here, the number of them grows exponentially, right? So it gets not ideal. And so for that reason, for really high dimensional things, maybe you have to approximate things by just having only polynomials in each individual variable as opposed to all possible cross products. But the point is, you can do it. In theory, you can do it. It's just that in practice, it quickly becomes kind of intractable. But I'm just going to talk about a single dimension, at least for the most of today.
So isn't there like some heuristic to choose, like what coefficients, like what terms you want in the polynomial?
Right. So the question is there a way to choose kind of which degrees of the polynomial I want? Sure, but you still have to form them all for a lot of heuristics, right? You can have things that incrementally add them as linear terms become selected. Then you try their combinations too, but none of them are sort of completely standard. There's lots of different ways people try, but there's nothing that's that standard. And to be honest, most of these things, if you need a really complex function class and can't figure out what it should be beforehand, you're probably better off using a neural network than trying to create crazy polynomials like this. So just do that. Sometimes, maybe. This part of machine learning is definitely, not always a science. Okay, so let's keep playing this game. So, degree 3 polynomial is a little better fit than degree 1. I guess I didn't show degree 2, but degree 2 by definition is a quadratic function, so it's almost kind of symmetric, or symmetric around some point, right? But let's just keep going. That's not going to be as good a fit because it's not symmetric, that thing. Let's just keep going and do higher and higher. So here's degree 4. That's looking maybe a little better. I don't know why it tails off down there, but it's getting to be outside of our data range anyway, so we don't really worry about pointing too much on the outliers. Here's degree 10, so that maybe a little better. Here's degree 50 now. It's probably not as good anymore. And so what's happened here? Yeah, so if you saw the title of the section here I'm talking about overfitting. Well, no, the next section, I guess, is about overfitting. Or is this section about overfitting? Next section is about overfitting. And so, in fact, before I actually get to that, I just want to make an interesting point here, which is that, and I didn't make a poll on this because actually this was the same as the poll was about yesterday, or Monday. But just to remind everyone, if you have the same number of features as examples, and if all your features, by the way, have to be actually truly different. So in the temperature case, we actually have some overlapping inputs. So, they discretize the possible temperatures. So we have multiple readings that are all, 80 degrees. But if you actually have non-overlapping points, then it turns out that polynomials form a set of linearly independent features, it turns out. I won't prove that, but it's not that hard to show. And so this least squares equation, if you have, for example, the same number of features as variables, so n equals m here, you actually can simplify that equation some. Because each of those terms, those x terms, are now square in the case of n equals m, and you assume that they're invertible because you have different input points, you actually can expand that inverse now, and some terms cancel, and you just get x inverse y. In other words, you always have x times theta equals y. So you've actually fit all your points exactly. And so, even though it might seem like a good idea to keep adding more and more features, it's probably not. The reality is you probably want to stop, even this is a pretty bad function, right? So you probably want to stop, and there are some 1,000 examples here. So you probably want to stop well before you actually get to your number of examples, because that looks pretty bad as well. So let's talk now in the next section about this phenomenon. You already gave the name for it. This is called overfitting. So we're talking about overfitting, generalization, and a couple ways to get around this, like a feature selection or hyperparameter selection, but also a concept called regularization. Okay, so I'm going to just try to formalize now what probably all of you already had the intuition for, which is the fact that what we really care about is not really what I've been talking about so far, right? So actually, this line here gets great loss on the training set for the loss that I defined, right? And in fact, what's happening on those points over there is it's passing exactly through those points. So the function I defined is actually hitting those points exactly, which is of course much better from a least square standpoint than doing this, because this is actually having some error on those points, whereas this has no error on those points. Okay. So what you quickly realize is sort of what you already intuitively knew, which is that this objective that we're optimizing is not actually what we care about. Right? This objective says I want to have minimum loss on my training set, but what we care about is really when I see some new data point that isn't in my training set, how well do I do on that? It's very easy to just memorize a training set and get everything entirely correct. The actual goal of machine learning is to be able to generalize to new examples that we haven't seen yet. That's kind of implicit in all of this, and I've kind of ignored this all so far. What we really care about is how well we do on examples that are in some sense drawn from the same distribution as our training set, but which are not actually in our training set. And we will analyze this a little bit more theoretically next lecture, but for now I'm just going to talk about it from a kind of an intuitive standpoint. And what's happening, as I'm sure people realize, is that the higher order degree polynomials, they are overfitting. In other words, they have very low error on our training set, but when we think about a generalization set, they have quite high error. I shouldn't say error. They have low loss on our training set, but on a generalization set, on the true underlying data, they actually have relatively high loss. And the cartoon picture to keep in mind, which again you may have seen before as well, is something like this. So as our model complexity increases, we almost by definition, and maybe assume now we actually can at least find the global optimum of these problems, so assume the problem is convex. But in that case, and in practice in most other cases as well, as the model becomes more and more complex, our training loss, which is again the thing that we're actually optimizing, is only going to go down. Right? And that's, if you add another feature, you can only decrease your training loss. Add another polynomial, you can only decrease your training loss, right? And that hopefully is obvious why that is. I mean, the class of all functions of polynomials of degree 5 is a strict superset of the class of all functions of polynomial of degree 4, right? You can always just set that last one to be 0, and that's the original function. So you can only do better by allowing yourself another knob to kind of tweak to decrease your loss here. So as you increase model complexity, your training error will always just keep going down. Eventually, it will become hopefully 0. Well, not hopefully, but often 0. And this contrasts with the generalization performance of the algorithm. And this will go down for a while because with a very simple model, you probably can't fit your data very well. But with a very complex model, you've probably overfit your training set. And so you're in a regime where your training loss is very low, but your generalization loss is relatively high. And what you actually kind of want to find is that sweet spot in the middle that actually minimizes your generalization performance. So the way you do this, again, it's hard to quantify the true generalization error because that's kind of this conceptual thing of if I draw from the same distribution, what happens. So what people do in practice is a technique called cross-validation, which is exactly, again, what you would think to do. Probably all of you have, it's the first thing you would guess to do if you thought about it. But all you do is you take your training data and you say, I'm going to split it into 2 parts. I'm going to call one my training set. I'm going to call the other part my validation set. And what I'm going to do is I'm going to train the algorithm only on the training set portion of this, and I'm going to then evaluate it on the validation set. Right? Because what I actually care about is my validation set, and so I'm going to use this data again. And actually, in theory, this is the correct thing to do because this is also drawn. As long as this is drawn from the same distribution, and there's certain independence, then this is an unbiased estimate of our true performance. making a lot of assumptions there, but that is, you know, in the simplest case, that would be the case. So this is what we do, right? It's a really simple technique that's incredibly popular, and everyone does this because it would be crazy not to do it. People make mistakes, but not this mistake. People do make mistakes, but it's very unlikely to, you know, see a paper or a report where people report training error and claim that to be a success. That's not a very common mistake. So this is a terminology thing now. I'm going to refer to the theta variables here as the parameters. I'm going to keep doing that. But I'm also going to refer to another class of parameters for our algorithm called hyperparameters. And these things are kind of, you know, the meta parameters that are not included in theta. Like, for example, what degree of the polynomial do I choose? Right? There's another one that's coming up in a second, which I'll talk about also. But in general, these things that are sort of features of my problem construction or features of my, you know, optimization problem. Maybe like what hypothesis class I choose is also kind of in some sense a hyperparameter. What loss function I choose is a hyperparameter in some sense. And all these I'm going to refer to as hyperparameters, though the most obvious here being just the number of polynomials, the degree of the polynomial we use, for example. And the basic idea of cross-validation is that we're going to use the training set to learn our parameters. So given a fixed set of hyperparameters, you know, a fixed number of features, a fixed loss function, etc., we're going to use the training set to find the parameters that minimize the sum of losses, right? But then we're going to use, but that, you know, is not a great proxy for the actual generalization performance. So we're going to choose the hyperparameters based upon the loss on our cross-validation set. I should add, there's no way you can use the training set to determine hyperparameters, right? Because again, if you add more higher degree polynomial, you'll just do better and better. So you can't use the training set to determine your hyperparameters, and you really want to use some separate set. And so we're going to use this cross-validation set to determine our hyperparameters. Questions there? Okay, so here's how it looks. So here is now my same training set before. I've just color-coded it in 2 different ways now. So my new training set is just the blue points, and my green set is just the holdout, the cross-validation set. And again, this was the cartoon picture here. This is what it looks like in a cartoon sense. Here's what it actually looks like when I increase the degree of my polynomial and look at the error that I have. So this is the degree of polynomial on the x-axis here, and the average squared loss on the y-axis, and that's a logarithmic scale on the y-axis. So actually, the training loss is still going down. This is actually still going down, modulo actually some numerical instabilities which happen when you talk about 50-degree polynomials, but it's going down the whole time. But very quickly, my holdout set starts experiencing really, really high loss, as you would imagine, right? Because, you know, a function like this, if I have some point, you know, that's right next to it, just doesn't happen to be exactly on that polynomial, it's going to suffer incredibly high loss. And so it's not going to be a good idea to try to fit it, model this function with a 50-degree polynomial. Zooming in a bit, this is what it actually sort of looks like in a reasonable range. This is now still a log plot, but it seems like, you know, anywhere between maybe 5 and 15, we're actually all doing pretty well. So this is a big enough data set where you can actually safely kind of fit a polynomial of degree 5 or 15 from 5 to 15 to this data set and get, you know, reasonably low error. Though you might also claim I don't really want to go above 3 because 3 is actually even simpler and you know, it gets still pretty low error. You probably don't want to have 1 and you don't want to have 2, but probably 3 is okay. Change at all? No, same thing. Okay, so I just want to mention a few more things because people mention these things, and I just want to mention what they are. So a variant of this is called k-fold cross-validations. It's where you divide your data set up into k different subsets. You train on all but one of them and test on the last one. Then you do that with a different one. Then you held out the second one, train on everything else, test on that one. Oftentimes people mistakenly call this cross-validation. Or refer to all cross-validation as k-fold cross-validation. That is k-fold cross-validation. The single holdout set is cross-validation in general. So just know that cross-validation is not just this, though this is a very common practice. Again, a few more variants. You can actually take it to an extreme and have a setting called leave one out cross-validation, where you actually have your holdout set be each individual example, and the training set is everything else besides that one example. And you do that for every example. Now, actually, kind of surprisingly, this is not hard to compute for least squares. There's actually a trick you can do with least squares to compute this with the exact same complexity as computing the least squares solution. You can compute the leave one out cross-validation error, which is kind of a nice feature of least squares, but that's really just for least squares, so you don't see this that often in practice. A couple other terms like stratified cross-validation. This is when, if you have a very unbalanced data set, you have maybe many more positive labels than negative labels, or vice versa. You want to keep the same percentage of positive and negative labels in your training set and testing set. Otherwise, you might run into these biases where if I happen to pick all negative examples in my test set, that will not be very indicative of my true performance. So that's called stratified cross-validation. And just a little warning, if everyone uses k-fold cross-validation, it's actually not necessarily any better than just normal cross-validation, theoretically and practically. There's oftentimes no reason to use it, so if it's simpler, or there's cases like time series where you actually always want to hold out later time points and have that be your validation set. You don't want to train on the future and test on the past. It's very easy to do things like that, but it's a very bad idea. It will not give accurate results or not be very indicative of how your thing will perform in the future. So there are definitely times where you don't want to use k-fold cross-validation. Okay, so that was just sort of a few minor things there about how you evaluate and practice generalization error. But I actually want to focus on another topic for the majority of the rest of the class, though I'll touch on a few other things as well. And that is one called regularization. So it seems fairly obvious to us that, the degree of the polynomial seems like a very obvious way to control the complexity of our hypothesis class, right? We just do that. If it's not too high degree, it won't be that complex. But there actually is another way as well, and this is something called regularization. So this gets at the following point. The way we were able to fit this crazy polynomial and have it exactly pass through the data points in our training set such that the training set had low loss. It turns out the only way you can do that is by having really high coefficients on your polynomials. That's not too hard to see, actually. I mean, if you just think about it intuitively, again, you can derive that from a linear algebra standpoint, but also just intuitively, I mean, you have to hit these things exactly, right? And how are you going to do that other than having, a really high weight on one, a really high weight on the other, so it cancels out, so that these, crazy terms all add up to be exactly a bunch of these points on, on the data. I'll go back to it. You have to have a lot of crazy coefficients to make sure it passes through all those points exactly, right? That's not very easy to do. And so if you actually look at the coefficients on the polynomial that I fit to that 50-degree polynomial that I fit to that data there, they are on the order of 10 to the 6th, 10 to the 7th. They're really big numbers, right? And you need that, even though my y-axis was on 1 to 3 or something like that, right? The coefficients end up being really, really big, and that's my x-axis was even on the 0 to 100. So these are really, really big numbers when we talk about x to the 50th times this thing, right? It's a really big number we're talking about. And so this suggests a different way of controlling the complexity of our model class through something called regularization. And the idea here is that we're going to actually penalize not just our loss function, but also the actual weights of our parameters themselves, the magnitude of our parameters. And the most common way of doing this is something called L2 regularization, where we just actually, where's my eraser? We take our standard machine learning problem, and we just add another term that penalizes the squared norm of our parameters. Again, that's the L2 norm. It's just the sum of each individual parameter squared. And so if we solve the same thing, if we solve this with a degree 50 polynomial, these coefficients are not going to be possible. They are going to, be quite, basically, for some setting of lambda, and lambda is essentially a trade-off parameter by how much do we care about loss versus how much do we care about this thing. For some setting of lambda, for sort of reasonable settings, there's just no value in making the things that big because it only decreases our loss a little bit, right? You sort of saw how the higher polynomials didn't actually decrease loss that much, but they certainly do increase the weights of our parameters a lot, and so we actually will not do that. And so really, I should kind of have clarified that this is actually the canonical machine learning problem. You know, I said it was the other one, but it's actually this one. It actually is minimizing the sum of losses on my training set plus some term that measures the complexity of the model. And this one's very common, though there are other ones as well. Actually, a very common one is use of the L1 norm here, which is some of the absolute values of the parameters. That has some nice effects as well. But really, this is by far the most common machine learning problem you'll see. And so actually, things like support vector machines, they were actually not just minimizing hinge loss, but minimizing a regularized hinge loss is the true support vector machine. And again, not again, but maybe just making this point, if we take lambda between 0 and infinity, in this case of it being 0, it's just the exact same thing as what we had before, just not caring about the weights at all. If we take it to infinity, that will actually lead to the fully regularized solution. We basically will always just choose lambda to be 0, or sorry, theta to be 0, because any change in theta would just give us huge costs, so we'll just choose a 0 solution. And by varying it in between, we can kind of sweep out the space of model complexity. As one quick example, turns out for least squares, just like in the setting before, there actually is a closed form solution to the least squares fit. You have the same objectives as before. Take gradients in a similar way. So the gradient of x theta minus y plus lambda theta. Gradient of this whole thing, rather, is just equal to, this is what we did before, it's x transpose x theta minus y, and then plus lambda times, well, actually, if you can kind of imagine it here, you know, if y is 0 and this is the identity, this is actually the same as this, and so you just, you know, set this to be the identity here, and so the gradient here actually ends up just being theta. Or you can derive that exactly too. It's not very hard to derive. Each term the only term that depends on theta I is a theta I squared. So you take the derivative and it ends up being theta there. I actually put 1/2 in front of everything just so I don't have to deal with that number 2 in front of everything. I don't know why we think it's nicer to have the 1/2 in the objective and then no 2 in the derivative, but that's the choice we've made as a community. We make this equal to 0. And this leads to the solution that, again, you move all thetas to one side. You have, I guess, a x transpose x plus the identity times lambda times theta. That equals x transpose y. And so theta is just x transpose y plus lambda inverse, x transpose x plus lambda I inverse, x transpose y. One other nice thing about this is that this actually avoids the issues of this matrix here being singular and non-invertible. When you add that lambda I term, you always make it invertible, and so you'll always find a solution now with Python. So that problem we had before where Python returned an error, that won't happen when you add regularization. And you probably want to anyway, because it probably is a good thing for your model in terms of the complexity to add some regularization. Yeah?
So what do you mean by model complexity? Because even with regularizer, you're going to have a high degree polynomial.
Yep.
The coefficients will be small.
Exactly. Let me actually illustrate that. Here is a 50-degree polynomial with no lambda. That's what I said before. So this is the no lambda, right? Here is the minimum of 50-degree polynomial when I have lambda equal to 1. It looks like this. So essentially, when I say model complexity, what I mean is I mean a measure of how complex a function you're going to generate when you actually minimize this objective here. Okay? And so you're right, it's still in theory a 50-degree polynomial, but when you actually solve this problem, you're not going to span really the whole space in some sense of 50-degree polynomials because you're constrained by this weight, by this regularization penalty as well. So yes, in theory it's 50 degree, but in reality, I mean, I guess in theory too, but in reality, it's actually only spanning a small subspace, in some sense, the set of all 50 degree polynomials, because most of them you just never pick, right? So it's not as obvious a restriction as the just reducing your dimensionality case, but it's just as important a kind of restriction of the class of allowable polynomials. I haven't even got my polls yet, so I better hurry up a little bit. Okay, so here's just a couple things. So here's now a similar plot of as we had with the degree of the polynomial in terms of the degree of the of the amount of regularization versus the error we get, again on a log scale. So here, as we get higher regularization, we have the more regularized solution, so that becomes essentially 0. Whereas when we go this way, that becomes less regularization. That means we're more like the raw 50 degree polynomial. And then somewhere in the middle here, though again, like the degree, for a pretty reasonable range, we kind of get good solutions everywhere in that range there. And so maybe you'll choose, lambda equals 0. Or sorry, not 0, 1, 10 to the 0 as your setting there. Okay, so what all of this kind of leads to in some sense, and I'm going to ask the poll question now, but what all this leads to in some sense is kind of a way to think about the complexity of algorithms and what you do when the algorithms that you have, aren't working as well as you hope they'll work, right? So, though this is a little bit of a shift in focus now, I want to ask the following question. And that is, how do you fix this algorithm? So one thing that actually is true and sort of as a matter of fact is that one of the real skills of machine learning is not just knowing the algorithms, it's being able to fix things when they don't work very well. So you run your algorithm on some data, it doesn't work very well, what do you actually do next? And so I want to give the following scenario. So I want to give a scenario where I'm going to train a linear logistic regression classifier classifier on some data set. I'm not going to even say what data set this is. And I'm going to plot the training. Oh, I said testing. I should have said validation there. Didn't mean to say testing. Use that word yet. Testing validation, training validation performance versus the number of samples. And our plot. So I'm varying here on the x-axis as I'm varying the number of samples I give to my algorithm. So I'm training it, only on the first 10, then on the next 10 to 20, then on 50, 100, etc. So I'm increasing the sample size. And I'm plotting my loss on the y-axis for both my training set and my validation set. And the question is, in this setting, what would I do? What should I do? Should I, and this is a multiple choice question, so you can say yes or no to any of these. Should I increase the regularization parameter? Should I decrease it? Should I add some nonlinear features? Should I remove some features? Or should I run a neural network instead of a linear classifier? Where we haven't said what that is yet, but a neural network is a really complex classifier that's very nonlinear with a lot more parameters. Okay, let me. Oh. All right, 5 more seconds. And we'll just go ahead and close it now. One vote disappeared just now, so that's concerning, but there, it came back. Okay, so let's see how people did. All right. So, people don't really know what to do, I guess, in this case. Which again is fine because that's the most common thing to do when you don't really know machine learning that well, is you just try everything and see what works, and it's might work, but rarely ever actually works. So let's go through them one by one. I think I'll actually spend a little time here and won't do the next one. The next one's kind of the opposite case, or similar but opposite case. I'll leave that open so we can do it because I want to finish up some other things. But okay, so increase regularization parameters. Who says we should do that? So that means make a bigger lambda. Can someone say why you want to do that? Let's up there, yeah. Yeah. Okay, so of the first two, people are a little confused on which one you do. But you definitely want to increase the regularization parameter here. So let's see if I can actually, sort of hard to show both these things, but I'll just talk about it. Okay, so we are in a setting here where we are overfitting. our training error, our training loss is actually quite good. It's a low training loss, but our test loss is quite high. This is the 50 degree polynomial case. Okay, so our test loss is too high, our training loss is quite low. We need to do something different in order to actually make sure that we don't overfit to our training set. And one way of potentially helping that, not guaranteed, it's definitely not, by the way, this is not guaranteed to work by any means. It could just do nothing. It could just, or rather, what it could do is it could just increase the training loss to be worse. And so everything, that's actually the most common thing you'll see when you just increase your hyperparameter. But you definitely don't want to decrease it. In decreasing regularization, all you're going to do is choose a more complex hypothesis, which is going to lower your training error even more, which doesn't really matter here because we're not tracking that. That's already plenty low. We don't really care about making that any lower, and so we're not going to really benefit from that, from decreasing regularization at all here. The next one was the possibility of adding or removing features. This one's a little bit more subtle than that. But actually, people got it wrong in the opposite way, because there are some subtleties here, and I actually would say that neither of these are actually completely correct. Both of them can hurt, or both of them can help. But again, adding nonlinear features here is probably not a very good idea. Again, more features are going to help us, let us perform a better job of minimizing this, which is going to further decrease our training error. And there's no reason to believe from this that would actually further increase the testing error, the validation error as well. Does that make sense to everyone? Now, there is always some possibility, depending on your choice of features, that we are actually using a 50 degree polynomial as our true output, and so we're regularized enough that once we add that one feature, everything will work. But it probably won't happen that way. Probably all that'll happen when you add another features is you just lower your training error more, and your test error will stay the same or get worse. Removing features, again, that can help for the exact same reason, right? This is the domain of the 50 degree polynomial. If we remove features, we can have now a 3 degree polynomial, so we actually can benefit. So this could be a good thing. And running a neural network, is that a good thing or a bad thing? Actually, can someone tell me why they think that's a good thing or a bad thing? Yeah.
Probably a bad thing to make it more complex.
Yeah, it's probably a bad thing. I mean, there's always a chance that your function is in some space that a neural network really can approximate well in your architecture. But really, ultimately, you're just picking a more complex representation class for your function, and that's going to cause the same thing as adding more nonlinear features or decreasing your regularization parameter. Okay, so the next one that I have, and I'm not going to do this because I only have 5 minutes left, so I want to touch on some other things. But I will open the poll, and so look at the slides if you want. One isn't going to be class participation because we're not actually in class when you're answering this. But if you're curious, with that other one as context now, do you think you can do better on this one, where you actually, in this case, have both training and testing loss look like this. So they both asymptote to a degree that's too high. And I have a few different options here. You can do things like add more data instead, or you can run it as SVM instead of a logistic regression. But let me open up that poll. You can take it as you want, but I'll leave it open for the next day or so. Okay, so just a few more words now. Because I want to touch on one thing. I won't mention classification too much, actually, because classification, fortunately, is exactly the same as regression. That's sort of the nice thing about this framework, is all we do when we want to do classification, and in the nonlinear case, is we take our classification loss function instead of our regression loss function and use that. So if we want to do a support vector machine, for example, we can run the exact same optimization problem, now with regularization, because now we learned what that is, so I'll add that on to the official SVM. And again, the only difference now is that X contains nonlinear features of the actual input. So again, here's the linear classifier on this data set here. Here would be a classifier with degree polynomial degree 2. That you can see the region is actually changing here. Here's degree 3. Here's degree 10. So you start to see that maybe I'm overfitting. There's no reason to think that there's some space up there that magically it's going to have all the tumors be benign. Probably looks something more like this. right? So again, you have the exact same issues of overfitting, even more so because of what you mentioned before. If you're taking all possible polynomial degrees, polynomials up to some degree, that will actually now grow, in this case, quadratically, but in the general case, it will actually grow with the dimension to the degree of the polynomial. It works like n choose d, right? Okay, so let me say one last thing. And just, this is, so I mentioned before that very few people will run an algorithm and report training performance. But this mistake is actually very common. So here's a common thing people do, is that they divide a training set into training and holdout sets. They pick their hyperparameters based upon the training and validation sets. They pick their hyperparameters like the regularization parameter or the number of features based upon the validation set. Given that, they train on the training set, and then they report the performance they get from this procedure once they've optimized their hyperparameters. So what is wrong with this procedure? From back there, yeah. Exactly. So the problem here is you're actually using the holdout set as a training set just for the hyperparameters instead. So think about an algorithm that just can pick any function you want, right? For the algorithm, the training does actually nothing, and you just somehow optimize some hyperparameters to get like the perfect fit to your holdout set. You've done the exact same thing as training now. You've just done it in a different way. You've called it something else. So we are still fitting the hyperparameters now to our holdout set. And so I guess I just said this, but imagine an algorithm that makes random predictions, and you just with some random seed, right? And your hyperparameters are random seed, and I'm just going to fit my random seed to the point where I'm going to predict well on my holdout set. That's not a very good indication of how I expect to generalize on the true underlying distribution. So the thing to do is actually exactly what was said. You divide the training set into a training set, a holdout set, and now I'll use the word test set. So I'll use the word test set now to actually test the performance of your data there. And the thing you should do is first pick your hyperparameter. First divide your training set into your sub training set and your holdout set. Training set to train your parameters, holdout set to pick your hyperparameters, and finally a test set to test only one time at the very end when you're about to submit the paper. You test one time to see, confirm your results, and then you send it off. And if you get bad results there, you throw it away because you've now invalidated your ability to ever look at that data set again. So now, okay, you're not going to do that. And this is a real problem, though, because it is actually very easy for, even with the best of intentions, with good-looking methodology, to allow for some leakage of that test set into your overall evaluation, right? So maybe you try different algorithms, and each one you optimize type of parameters for on the training set, but I still pick the best algorithm on my test set, right? Or maybe I just make some very, after I've seen my performance a few times, I make some very kind of subtle assumptions that you sort of modify how I run the rest of my algorithms that are in fact influenced by the test set. So you can actually get away from this. You can do things like collect a new test set each time you want to run a new evaluation. But again, that's kind of a pain sometimes. So again, the best solution is that in practice, just if you can, test your procedure sort of on real data generated in the wild or from the true distribution. Look at the test set as little as possible, and don't really don't try to peek under the hood as much as you can. And recollect data if you need to, if you suspect you're overfitting. A lot of studies in a lot of disciplines have been eventually invalidated because of this problem here. I should add one thing, though. If people are looking for research projects or for class projects, there's a very interesting level of research called adaptive data analysis that actually uses techniques from differential privacy to guarantee that you will not overfit with some theoretical guarantees, guarantee that you will not overfit to a validation set. So there actually is so starting to be some theory about how you avoid this, but again, the practice is just don't do it too often, and you'll probably be okay. And be skeptical of your own results. All right, next time we'll talk about the theory behind all these things.